5D, counting. Okay, so when we're talking about counting in statistics, we're literally doing that. We're counting the number of ways that things can occur. We're not counting the probability. We're just looking at the number of ways that something can occur. Now, the fundamental counting principle tells us that if our first event can happen n ways, and our second event can happen m ways, then if we multiply those two together, we find out the total number of possible outcomes. What do we mean by that? Well, let's say we flip a coin and roll a die. Flipping a coin, there are two possible outcomes, heads or tails. Rolling a die, there are 6 possible outcomes, 1, 2, 3, 4, 5, and 6. So therefore, the total number of possible outcomes if I flip a coin and roll a die is 2 times 6, or 12. Well, if you don't believe me, let's take this next step and look at it. We're going to create a tree diagram. A tree diagram allows us to map out these different occurrences or these outcomes. And it allows us to get the sample space of the outcomes, so the list of all possible outcomes. So let's start by flipping a coin. So we've got a possibility of getting heads or tails. Our first event, flipping a coin. Our second event we're going to put below it, that's rolling a die. Well, if I get heads, 1, 2, 3, I can get a 1, a 2, a 3, a 4, a 5, or a 6 when I roll the die, or I get tails. I can get a 1, 2, 3, 4, 5, or 6 from that die. So my sample space of all possible outcomes is heads 1, heads followed by a 2, heads followed by a 3, heads followed by a 4, heads followed by a 5, heads followed by a 6, tails followed by a 1, tails followed by a 2, tails followed by a 3, tails followed by a 4, tails followed by a 5, tails followed by a 6. And that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes. Now notice that I abbreviated these outcomes. I didn't take the time to write out all 12 possible outcomes. If you decide to abbreviate a sample space of outcomes, you have to give at least 3 values or outcomes in the sequence to show the pattern, comma, ellipse, that dot, 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 another comma, and then you should give your final outcome also, if it's a finite series. In this case it is, it ends at that, there's only 12 items. So we list that out. Remember that when you use a tree diagram, you are using that to find the sample space, usually, or if you're asked for the sample space, remember that's the list of outcomes as opposed to the total number of possible outcomes, which is what we found with the fundamental counting principle. So I found out there were 2 possibilities for flipping a coin, 6 possibilities for rolling a die, therefore a total of 2 times 6, or 12. Using the fundamental counting principle, what if I were to, well, let's be bold and daring. Let's say I pull 5 cards from a deck. So I'm getting a full hand of cards, 5 cards. How many possible outcomes are there? Well, if I'm getting a handful of cards, I'm not putting the card back in, right? Otherwise, I'd still only have one card in my hand. So it's got to be without replacement. So there are 52 possible cards for the first card, and then there's 51 for the second card, 50 for the third card, 49 for the fourth card, and 48 for the fifth card. So we have 52 times 51 times 50 times 49 times 48. So 52 times 51 times 50. Sorry, I hit a wrong button. 52, 51, 50, 49, 48. So that's 3, 1, 1, 4, sorry, 8. Rough day writing on the board. 8, 7, 5, 2, 0, 0. Or essentially, there are 311,875,200 arrangements of 5 cards that I could get. Wow, that's a lot. So that leads into the next topic, which is permutations and combinations. What? Permutations and combinations. So we're going to start with permutations. I'm going to tell you that in permutations, order matters. In permutations, order matters. So many times when we deal with permutations, we may use the word arrangements. Arrangements, right? In an arrangement, order matters. If you have a floral arrangement, it's not just a bunch of flowers thrown in a vase. It's organized in a way to be aesthetically pleasing, right? You can have the same flowers stuffed in that vase and have them just look like a mess of flowers in there, or you can have them look very elegant by the arrangement of those flowers. So permutations, order matters. Now, if I take n items, and I want to know how many ways can I arrange n items, that can be found by taking n factorial. If you're not familiar with this exclamation point, that's called factorial. And what it means is to multiply n times all the numbers less than it down to 1. So n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 all the way down to 1. So if I say n is equal to 5, if I have 5 items and I want to know how many ways can I arrange 5 items, I can arrange them 5 factorial ways, which is 5 times 4 times 3 times 2 times 1, which is equal to 120. So how many ways can I arrange 5 items? 120 ways. So n factorial. Anytime you want to find out how many ways you can range a set number of items, n factorial. Just take whatever number is. If I want to arrange 10 items, 10 factorial. If I want to arrange 48 items, 48 factorial. So that's if I'm taking all of them. But we don't always want to arrange all of them, do we? In fact, the example that we did previously, when looking at how many possible arrangements of cards could we have if we pulled 5 cards, we didn't look at all of them. We only looked at the first 5 of 52. different cards that I could be pulling. So when you're dealing with permutations, we use NPR. P stands for permutations, N is the number of items, and R is the number taken. So N items permuted R at a time. So if we have 8 items and we're only taking 3 of them, 8P3. So how do we do that? Well, we always start with how many ways can we arrange everything. So that's n factorial. And then we divide out what we don't care about. Well, if we're only taking R of them, then the difference between n and R are the ones that we don't care about. So n minus R factorial. Say that again, Mr. Davis. What are we talking about? Well, what if I have 8 items and I'm only going to select 3 of them? Let's say I've got 8 students, and I'm going to randomly pull names from the hat, but I'm only going to pull 3 names. The first person, I'm going to give an A in the class. The second person, I'll give a B in the class. The third person, I'll give a C in the class. And the other 5 students all fail the class. Okay? So if I'm looking at that, what really matters are who the first 3 students are. The other 5, who cares? It doesn't matter what order they're selected, they're all getting Fs. But the first 3 matter because it's the difference between an A, a B, or a C. So how many ways can I arrange all 8 students? 8 factorial. Well, I want to get rid of the ones that I don't care about, so 8 minus 3 factorial gives us 5 factorial. So basically, we're starting out with how many ways can we arrange all 8, and then we're dividing out the arrangements of the people who don't get an A, B, or C. So 8 factorial, 40,320. 5 factorial we already know is 120. Gives us 336 ways that 3 people can get the A, B, and C. So that I can arrange 3 out of those 8. So that's what we're looking at there. Well, let's look at it another way. How many choices did I have for the A? I had 8 people. How many choices for the B? 7 people, because 1 received the A. How many choices for the C? 6 people, because I already gave out the A and the B. This is the fundamental counting principle, right? How many choices for the first one, how many choices for the second one, how many choices for the third one. 8 times 7 is 56. 56 times 6 gives you 336. Got the same answer. Let's look at here. I'm going to switch to a different color for this, just to, so it shows up more. We have 8 factorial over 5 factorial. Well, isn't 8 factorial 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1? And 5 factorial is 5 times 4 times 3 times 2 times 1. Well, now this is multiplied together. That's multiplied together. Can't I pull out common factors? Get rid of the 5s, get rid of the 4s, get rid of the 3s, get rid of the 2s, get rid of the 1s. And what am I left with? I'm left with 8 times 7 times 6, which is what we had here, which is 336. So permutations of n items taken r at a time. Well, since we know that, let's look at something relatively simple. Let's look at the name Bob. Always been a fan of Bob, okay? Works well for me. How many ways can we arrange the letters in the name Bob? Arrangement, we're talking about order, permutations, and we know that if we have 3 items, and we're trying to find out how many ways we can arrange those 3 items, that's n factorial, so 3 factorial is equal to 3 times 2 times 1, which is 6. So there are 6 ways that I can arrange the letters in the name Bob. Okay, so let's list them out. So there are my 6 ways that I can arrange the letters in the name Bob. Well, what's the problem here? It should be pretty obvious. We've got duplicates. These 2 arrangements are not distinguishable from one another, but they are different arrangements, because if I treat this as the first B and that is the second B, now that's the second B and that's the first B. If I treat that as the first and second B, now that's the second B and the first B. If I treat this as the first and second B, that's the second B and the first B, right? So, although I can arrange the letters in the name Bob in 6 different ways, visually, there are only 3 distinguishable arrangements. Distinguishable arrangements, meaning ones that we can tell the difference. You can't, if I just write them up here, you can't tell the difference between OBB and OBB, right? So, distinguishable arrangements, when we calculate distinguishable arrangements, we always start with all of the ways we can arrange everything, n factorial, and then we divide out what we don't care about, and what we don't care about now are replication. So I'm going to call it n sub 1 factorial times n sub 2 factorial times n sub 3 factorial dot dot dot. So basically, duplicated values, we can't tell the difference between them. So we're going to get rid of the arrangements of those. Next set of duplicated values, we're going to get rid of the arrangement of those. Next set of values, we're going to get rid of the arrangement of those. So in this particular case, we're going to start out with 3 factorial, and then we're going to say, okay, there are 2 B's, so we're going to divide out 2 factorial, and there's 1 O, 1 factorial. Now I will tell you that in general, I tend to leave out the 1 factorials because 1 factorial is 1. 1 multiplying down to itself is 1, right? So it doesn't really tell us much, so if we have just a single case of something, it's usually advantageous to just leave it out. But now we have 6, 3 factorial is 6, over 2 factorial is 2, or 3 distinguishable arrangements. 1, 2, 3 distinguishable arrangements. Let's make that a little more complicated, meaning Bob was kind of simple. How many distinguishable arrangements can we make with the letters in calculator? So how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So how many ways can we arrange them all? 10 factorial. Then we look and there's 2 C's, 2 factorial, there's 2 A's, 2 factorial, there's 2 L's, 2 factorial, 1 U, 1 factorial, 1 T, 1 factorial, 1 O, 1 factorial, and 1 R, 1 factorial. These are multiplication signs, multiplication, multiplication. But you see how annoying that is, putting all those 1 factorials in there, since we had 1 T, 1 O, 1 R. Did I get one extra? No, there was the U. There we go. 1 U. So we had 4 of those. So we can just get rid of those because 1 factorial is 1, so who cares? So we end up with 10 factorial over 2 factorial times 2 factorial times 2 factorial. So let's find out what 10 factorial is. That is 3,628,800, so 3,628,800. And then, now I want to point out 2 factorial times 2 factorial, so let's just do this. 2 factorial times 3 factorial is not equal to 2, sorry, that's not a 2. 2 times 3 factorial, okay? You can't take what's being factorialized and multiply it together and then take the factorial. It's not the same. 2 factorial is 2, 3 factorial is 6, 2 times 6 is 12, 2 times 3 is 6, factorial, going to be much higher, 720. So that's all that over 2 times 2 times 2, because 2 times 1 is 2, or all of that over 8, 3,628,800 over 8, which gives us 453,600. So 453,600. The number of distinguishable arrangements. If these were just 10 letters, no duplicates, then we would have 3.6 million possible arrangements. But if we have duplicates like we do here, in this case, we went down to less than 500,000. So quite a difference there. We went to less than 1/7 the amount of possible arrangements because of those duplicate letters. So that's permutations. So let's just do a little recap here of permutations. So permutations n factorial, how many ways to rearrange n items. NPR is equal to n factorial over n minus r factorial. And then distinguishable arrangements is n factorial over n sub 1 factorial times n sub 2 factorial times n sub 3 factorial. Dot, dot, dot. Continue on however many there are. So permutations. Now what I'm going to bring in is combinations. Combinations, order does not matter. Order does not matter, and we sometimes use the word groups for combinations. If you think about it, you may have a group of friends. The order of the friends doesn't matter, they're still in the group. right? If you have a grouping of something, we don't care about the arrangement. We just care that they're part of it. If you're put in a certain work group, or you have a study group, you have a group, number of people, they get together, it doesn't matter the order, you're just all part of that group. And that's what combination is doing. So combinations is like permutations, except that now we don't care about the order of the people who, or the members that become part of the group. So it starts out, and I'm going to put NCR, n items combined R at a time, as opposed to permuted R at a time. Realize that there's no equivalent to n factorial with that, because if you take 10 items and create a group of 10 items, there's only one way that can happen, so it's a moot point. So there's no equivalent of n factorial. But if we're saying how many groups can we make from n items taken R at a time, we start out as always with n factorial. How many ways can we arrange all of them? Then we divide out what we don't want. Well, we don't want the people who don't make it into the group. So that's n minus r factorial. So far it looks like permutations. The only other difference is now we don't care about the order of the people who made it into the group, times r factorial. So this is the order of the things that did not make it into the group. This is the order of the things that did make it into the group. So NCR. So now, what if I want to see how many groups of 3 items can I make from a set of 8 items? So we have 8C3. Well, we start with how many ways can we arrange all of them? 8 factorial over, get rid of the ones we don't care about, so 8 minus 3 factorial times 3 factorial. Well, that's 8 factorial over 5 factorial times 3 factorial. 8 factorial was something like 40,320. 5 factorial is 120. 3 factorial is 6. So we got, just to make sure, yep, 40,320 divided by 120 times 6 is 720, which gives us 56 groups that could be made taking 3 items out of the 8. So I put all that up there, so now you can see the permutation formulas, the combinations formula. So it's very similar to permutations. So the only thing I have left is I want to use permutations and combinations to determine the probability of something occurring. Okay, so what I want to look at here is, I want to find the probability that I get a royal flush when I'm dealt 5 cards. A royal flush is a straight that includes the cards 10, Jack, Queen, King, and Ace. That's what makes it royal. And the flush means that they're all of the same suit. So they're all hearts, or they're all spades. So a royal flush, they're all the same suit, and it's 10, Jack, Queen, King, Ace. So I want to find the probability of getting a royal flush. And I'm going to use counting to do that. So I want to know, how can I get a royal flush? Well, it's going to take 5 times drawing a card, and the first card that I draw, I've got 20 possible cards that will make me happy. What am I talking about 20? Well, there's 10 jack, queen, king, and ace, 5 cards, and there's 4 different suits that I could get this royal flush in. So I've got 4 times 5, or 20 cards possible to start me on my royal flush. Now we have to be careful, because once I get a card that starts my royal flush, all of the other cards have to match that suit. So that means instead of having 19 cards left, once I've got this, there's only 4 other cards in that suit that will finish off my royal flush. If that's a king of hearts, then there's just the 10 of hearts, the jack of hearts, the queen of hearts, and the ace of hearts. So I've eliminated that, so that means my second card, there's only 4 possibilities. Now, once I've got that suit, it's going to fall down, so the next card, there's 3 possible cards left, 2 possible cards left, and 1 possible card left. So that'll give me the number of arrangements of cards. That will give me my choice. So 20 times 4 times 3 times 2 times 1. Now, in the denominator, I need to look at the number of cards available. So there are 52 cards initially, 51 cards after that, 50 cards after that, 49 cards after that, and 48 cards after that. Now, you could look at that and say this specifically here is the same as 52P5. Right? We've got 52 cards to select from. We're going to select 5 of them. The order matters. So now that I've used the fundamental accounting principle, or I've used permutations, it's a matter of doing the calculations. So the top should be 480, 20 times 4 times 3 times 2. 6 times 4 is 24, 24 times 20, 480. The bottom, 52 times 51 times 50 times 49 times 48. Those are 311,875,200. So 311,875,200. So the probability of getting a royal flush is 480 over 311,875,200. So let's divide that. And we get the probability of getting a royal flush is 0.0000015, approximately. 0.0000015 probability of getting royal flush. That's not very likely. Okay? But that's it. So that's using our accounting, fundamental accounting principle, permutations, combination, whichever, to come up with a probability. And that finishes up counting.